This will be a live coding session, and it will be in 2 languages. So I will have a Haskell file because Haskell is lazy by default, and JavaScript because it also has features that can make it lazy. So we will switch between those 2 quite a bit. So what is laziness first? So for this, we will first jump to the JavaScript file because that's what probably most of you are familiar. So if I have a statement, for example, I have some array, and let's say I have 1, 2, 3, 4, and then I call .map, or maybe .filter x, and now x modulo 2 equals 0. We only have even numbers, and then we square them, doesn't matter what we do. And then I do console log test, string test. So when we execute this JavaScript file, it doesn't matter if we do it in Node.js or in the browser, execution starts at the top. It comes here to this variable or this constant, and it will execute this, then it will execute this filter function, it will execute the map, and then at this point, this whatever variable or constant contains 416 as an array. So I can see here, oops. So if I'm not, yes, it should be that. And then we log something to the console. This doesn't matter if we use this or don't. Same thing if we now define a function that takes an argument and just returns null like any good function. And I call foo with something like this. Before entering into the function, so here, at that point, x is already 2, 4, 6, 8. So at that point, it is already evaluated. So before entering into foo, this expression, what is in here, will be evaluated completely. But you see, in the examples, neither do we use this constant, nor do we use that this expression in the function. So in theory, this computation is for naught. We don't need it. In the end, the only visible effect to the outside is that we write tests to the console. So any of this code before that is completely useless. That's also where laziness comes in. It's basically do the least amount of work needed to actually do the job that we can observe in the outside. Yeah. So if we would translate all that code into Haskell, we would see basically it does nothing of those. We would only see the hello world that we have here. The reason why this is Haskell is lazy by default, so every expression is lazily evaluated. And this is, I think it's the only language that does this. So if I have, for example, a constant whatever, and the same thing, I mapped a lambda function, where is that? And I square the number and then 1, 2, 3, 4, whatever. At that point, what Haskell does is, okay, it realizes that, okay, there is this constant, and it does not evaluate it. It basically just has, okay, this is a func now. Func is basically a piece of code that tells Haskell how to evaluate what. So at this point, this is not this here. Oh, let's go one line further down. Whatever is like func. And func is basically a function. So when we need now actually this whatever, then this func would start to evaluate. So and only until we need it. So if we only need the first 2 elements, like there's no need to evaluate like this square function, which could be potentially expensive. So don't know what it does. Heavy computation doesn't matter. It would be wasteful to like, okay, I need 1 element. Let's compute it for all the elements. Exactly. That's also, for example, the sorting function in Haskell is lazy. So that means if you only need to get the lowest element in a sorted list, so you say, okay, you sort the whole list, and then you only take the first element. Would be wasteful in any other language, but in Haskell, it just takes like the smallest element and leaves the rest unsorted. And the further, like if you need all the elements, you will have a completely evaluated sorted list. But if you don't, you will only sort until the point where you need it, which is quite fascinating. So what I want to show you today specifically is FizzBuzz. So what is FizzBuzz? Probably most of you know. Basically, we print the numbers from 1 to 100, but we replace every number that is divisible by 3 with fizz, every number that is divisible by 5 by buzz, and if a number is divisible by both 3 and 5, we say FizzBuzz. So it would basically go 1, 2, then it's divisible by 3, so we say fizz, 4, then it's divisible by 5, buzz, then again 5, and then a bit later when we have 15 we get FizzBuzz, because 15 is 3 and 5, and so on and so on. So this is, it's a very simple programming challenge, and usually the solution is, okay, we loop through the numbers and then check if the number is divisible by 5 or 3 and then do something. But the lazy solution I will show you today will not check anything. The main idea is to use infinite lists in Haskell or generators in JavaScript, which could be seen as infinite lists. So because it's lazy, Haskell doesn't have a problem when a list is infinite, because it will not evaluate the whole infinite list at when you write it, so but only as far as you need them. So to have a list of all the natural numbers in Haskell, which are infinite, as probably evident, you can just write, okay, you're starting with 1, and then so this is a range in Haskell, so this would be a list from 1 to 4. But if I just leave out the last number, this is now a list from 1 until infinity. And this is fine, so this won't crash the program. If I try to evaluate this, so this, I will show this too. So if I, oh no, I need a second screen for that. Let's make it also big as hell. So this is the Haskell REPL. And if I load now the file, it compiles, it's fine. And if I would now want to evaluate all the natural numbers, like this would, it goes on and on. So I need to abort it with Control-C. Yeah, you see they're interrupted because it would go on forever. I try to evaluate an infinite list. Yeah, that's the main thing. Let's hide this for now. We only need that. Okay, so FizzBuzz, how do we do this? Well, the other interesting thing is we can basically say, well, we want to repeat a pattern. So I could write a function, cycle, and let's say it takes some list and it returns an infinite list. And this cycle, so we take some list as argument. So this is a function. And we say, okay, we have a helper function, go, we call with that list. And this go is defined as the following. So if we have an empty list, then we use the original list we passed in again. For the other case, if we have at least one element, so this is basically, this is the empty list, and this is one element followed by the rest of the list. So these are the two cases we can have. We either have an empty list or we have at least one element and possibly more. Then we will use that one element and continue with the rest of the list. So this way, if we mentally evaluate cycle for 1, 2, 3. So first, this go will hit the second case because we have at least one element. Let's make the list a bit smaller, a little bit easier. So first, the second case will hit. So it will return, it will be, so go, it will call go of 1, 2. And then go uses the second case here. So it will return 1 followed by go of 2, which again is the second case. So it will be 1, 2, followed by go of the empty list. And at that point, the first case hits here. So it will return, this stays the same because we are just replacing this part here. So this in parentheses, we are replacing that part now. And we're replacing that with go of the original list, so 1, 2. And then we further can continue. Now the second case hits again. So we have 1 and go of 2. And you see the pattern here. Like this pattern repeats infinitely. So what we effectively do, we can remove the parentheses. That doesn't change the thing. So what we effectively have done is a function that takes a list as input and then just repeats the list infinitely often. So it will be 1, 2, 1, 2, 1, 2, forever. Or written in list syntax, it's 1, 2, 1, 2, 1, and forever. So this is what this cycle function does. And with that, we can easily create infinite lists of some repeating pattern. And the pattern we want to repeat is if we have we want to now have buzzes. So buzzes is all our buzzes we will need for our FizzBuzz. And buzzes is just we cycle an empty string, another empty string, and buzz. And recycle this infinitely often. And then we need all the fizzes. No, this is the fizzes, sorry. This is the fizzes. Now we need the buzzes. The buzzes is the same pattern, basically. We have an empty list, another empty string, another empty string, and the buzz. And also this pattern repeats infinitely often. But you see already, now we have like basically this pattern. This is the 4, and these are the 3s. So now we just need to combine those. So we want to take always one element of each list and combine it. So we write a function that can combine lists. So this function is called zip with, and it takes a function that takes 2 arguments and returns a third. It takes a list of the first argument, it takes a list of the second argument, and returns a list of the third argument. So it's basically just, yeah, always using one of the things. The definition, we can have basically 3 cases. The first case is our first list is empty. Then we don't have an element to combine, so we would just return the empty list. These underscores is basically ignore the other argument. So we are ignoring the function, and we are ignoring the function, and we are ignoring the second list. So this list here, this is the third argument. So then the other case is if the second list is empty, we also just return the empty list. We need 2 elements to actually call this function. This needs 2 elements to call. So the last case that is now open is when we have 1 element at least in the first list and 1 element at least in the second list. And now we have 2 elements that we can use to call our function with. So we call the function with the 2 arguments, and then just continue f, and then the rest of the first list and the rest of the second list. So this is just zips, always takes like the first 2 elements of the list, combines them, and returns them in a new list. And again, this is lazy, so it will only combine as far as we need. And because we only combine as far as we need, those that we so the original list will only be evaluated as far as we need them. So we can, without problem, use zip with infinite lists, because it will again be an infinite list, but it will do the right thing. So we can have our words is we zip with, and then we use the string concatenation. So in JavaScript, this is just plus. So string A plus string B is both strings concatenated. In Haskell, it's the plus plus. And we use the fizzes as first argument and the buzzes as second argument. This already gives us the FizzBuzzes. I can also already show you. The thing is, for example, zip with is already defined in the standard library. So I will first need to import the standard library and hide zip with cycle words. I think this is all yes. Just hide those functions because they are already defined. So if I go now back to our REPL and reload the code, everything compiled fine. And if I evaluate the words now, again, it will be infinite. But you see already we have some fizzes, we have some buzzes, and we have some FizzBuzzes, just because this pattern repeats as expected. To not have to interrupt this now always to evaluate it, we will write something that we can just take some amount of this infinite list. Again, this function is already defined, so I will have to hide it. But I want to show how it works. So take is rather simple. We take how many elements we want, an integer, and some list, and we return another list with that has only as many elements. So we have 2 cases. Either the list we get is empty, then we can do nothing instead of other than returning the empty list. The other cases, we have a 0, so we have no elements to take anymore. Then also we return an empty list. And the normal cases, we still need to take n elements, and we have a list with at least 1 element. So we take that 1 element and take n minus 1 elements from the rest of the list. So this cuts down a possibly infinite list to a finite amount of elements. So if I load that now in the REPL, I can now say take 10 from our words. And you see here I get a list with 10 elements. And you see fizz on the third space, buzz on the fifth space. Let's take a bit more. Let's take 16. And you see also FizzBuzz on the 15th point there. So this is already doing what we want, but we still need the numbers. But as I already hinted to earlier, we can easily define a list of all the natural numbers. We could also define these a bit different, just for you to see. Starting with some beginning number, we could say, okay, well, this is basically, we take that number, and the rest of the list is that number plus 1. So this calls, again, itself. Basically a function, it takes an integer and returns a list of integers. You give it a starting value, and then it takes that starting value, and then it gives you that list with one more, and this is again infinite. This is basically just syntactic sugar for basically the same thing. So if I put not one hard-coded there, but n, these are now doing exactly the same thing. But let's use that fancy syntax because it's nice. Okay, so what we want to do, we have already the words, so then now we just need to FizzBuzzes. So our FizzBuzzes, we again combine the words with the numbers now. So we are zip with, and now we get two arguments. We get the word and the number. And what we want to do is, if the word is empty, then we want to have the number, but we need to convert the number to string. So show converts anything to a string, yes. Else, we want to just show the word. And now my formatter should make this, I need to, make this a bit nicer. So let's put a line break here. And then through the magic of auto formatting, it will look nice. So yeah, so if the word is empty, as we saw, if we saw here, we have empty word fizz, empty word buzz. So we just need to replace the empty words with numbers. So if the word is empty, then we show the number, else we show the word. So now we have the FizzBuzzes, and again, we can do the same trick as earlier. We take 15 of the FizzBuzzes. We first need to reload our account. Oh, what did I do wrong? I need to, it is not sure what our numbers should be, because they're different. It could be floats, it could be strings, so I need to say that this should be integers. Now, what's the problem? Oh, I forgot to put the lists here. Yeah, I need to, I want the words and the naturals. Natural, let's call it naturals, it's multiples. Naturals, like that. Yes. So, I forgot the two arguments to zip with. I only provided the function, but not what should the list to be combined. So now we can again take 16 of the FizzBuzzes, and it's basically what you would expect. 1, 2, fizz, 4, buzz, and it does not check any thing. So now we could, instead of how our main function, so if we call main, that's our main function, it prints hello world. Let's make it do something similar to what the actual solution is like. So we want to basically have a for loop, but in Haskell, for loop is not part of the syntax, so we need to import it. So that's our for loop. And we'd say, okay, take 100 from the FizzBuzzes. And then let's make a new line and make this big again. And then for each of those, for each result, print that string. And because this is a bit redundant, we take an argument and apply it immediately after. We can just shorten this to string line. So basically this says 400 of the FizzBuzzes, print them. But you can just read it like that. Okay, then let's make this small again, reload our account, and run the main function. And it's what this solution would be. as one expects. So 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz. And with 15, there's the FizzBuzz. So this is the solution in Haskell. But usually people don't use Haskell for their daily job. So what can we do in languages that are not Haskell? We can basically just translate this thing word by word and put it into JavaScript, actually. So JavaScript has something that's called the generator function. And it's a function with a star, and with that you can return multiple values. But it's just this lazy list thing in disguise. So I can say function foo, and I say yield 1, yield 2, yield 3. And this is basically the same thing as in Haskell, a lazy list of 1, 2, 3. But in JavaScript, if you just say 1, 2, 3, it's eager. So that's why we need this generator function. And so let's just translate, for example, this naturals directly into a generator function. So, and I will use the second form I showed you with the starting value. So I have some starting value n. I yield n. And as before, I will yield, but I now need to yield multiple. So a function returns an iterator. It's a technical thing. If I want to yield a single thing, I need to use yield. If I want to yield multiple things, I need to yield star. It's not completely correct, but that's how I will go for now. So if I basically want to yield all the values in another generator, I need to use yield star. And because foo is a generator function, I need to use yield star. This is basically the same thing I showed you in Haskell earlier. We have the first value and then all the rest of the values. And this is now not called foo, but this is now our naturals. Naturals, yes. So cycle, and we'll just copy this for reference. And then again, we can very mechanically translate this. So we have this outer function cycle and this inner function go. We will have the same thing. We have an outer function cycle that takes the list. And I will, for clarity, I will call it outer. And we have an inner function go that is not accessible to the outside, but we need it for the recursion. So in the inner thing, we have the first case where the list is empty. So the first case is if we'll use arrays for this one. If inner.length equals 0, then we are in the first case. Then we call go, or in this case, we yield multiple go of the original list. So this is the original list. The original list we have here, original list. We go with the original list. Same here. If the length is 0, we go with the original outer list. Else, we are in the second case of go down here. And then we first yield that single element. So that is now inner of 0. So the argument to go is an array. We first yield the first element, and then we yield go inner dots, and we remove the first element from the array. This is not performant, but I'm just showing this for how this works. So this is just one-to-one translation. This is first element and the rest of the list. First element of the array, rest of the array. This is now the function go. And here we just need to call it go for the first time with outer. And then I can, which is same here. So to start off the loop, we call the go with the original list once. So let's remove this reference. And we also want directly to have something that can take an arbitrary amount, so can we easily show it in the console. So if I take how our take function is defined, again, I can copy that over. Again, this will be a generator. It takes an n. It takes a other generator. And then how generators work, if you work with them, they have a function called next. So in Haskell, this next is implied. If you use this is basically an implicit call to next. In JavaScript, you explicitly need to call next. So here, the next element is this generator.next. And this will return an object that has a done property and a value. So if the generator does not produce, so in Haskell, the empty list would be done true. And if there is still elements in the list, this would be done false and with the value here. So what we want to do, either we have the empty list, so if next.done, or so covering the first two cases down here. So if we have the empty list or a 0, if we have the empty list or 0, then we just return. If you just return nothing for generators, this is basically the empty list. It will return this done true value undefined. Else, in the case we do have, this is then this case down here, we take the first element, so this is then next.value. So this is here this x, the first element, we return that. And we return take with n-1 and the generator. And this is where the generator is stateful. So in Haskell, we have split the list argument in the element and the rest of the list. Here we call this, and this changes the state of the generator. So if we want to reuse this generator, this is now one further in the list. So this is the difference. But now I can again delete the reference. It works exactly the same. If I go now for const x of take 10 naturals 1, console.log x. This basically here, we take our natural numbers starting from 1, we take from them 10 things, and then I can probably, I hope this works, Node.js. This is a Haskell comment. Yes. So as expected, we get a for loop. This for off syntax works with generators too. So any iterator can be used here. So this is why this generator function works in this for off loop. We take 10 from this infinite list. If I just use the naturals here, so for off and remove the take, the same thing happens as in Haskell. This is now an infinite loop that will just print numbers to until I get a call stack, because I used recursion here. Haskell doesn't really have a call stack, so Haskell can go forever. But that's because here this is a recursive call to naturals, and JavaScript has a call stack. If I would define this with a loop, this would truly be an infinite loop. Okay, but we don't want this. We just need the first 100 elements. So what does this not? This is still meeting the cycle function we have now. We have take. So the next thing we need is to combine two. Again, we will take this as our reference. Make this big again. And implement it just as it stands there. We have zip with. It takes a function. It takes one generator, it takes a second generator, and it returns something. So we first again need to check the two values. So next one is gen1.next. This is the thing that's a bit annoying on generators. It's very explicit because it's bolted on instead of built into the language. So now we can check if we have two empty lists, or in generator speak, if we have two done generators. So if either next.1 is done or next2.done, then we finish. We just return an empty list, basically, an empty generator. And for all other intents and purposes, we are in the third case. So we have two values now. We can yield the function called with next1.value and next2.value. And then we yield the rest of the list, which is again a call to zip with the function. And again, because this generator stuff is stateful, we pass the same generators as before. Yeah, same thing as the Haskell code. So now let's use it. We have FizzBuzzes. FizzBuzzes is cycle of empty list, empty string, and is. And the buzzes is cycle of the empty list, empty string, empty string, empty string, and buzz. And then the words is zip with And again, we take a function here. So we say it's the 2 words, and we just want to concatenate the 2 words. And the first argument is the fizzes and the buzzes. So here, zipwith is a function call with an arrow function that combines the 2 strings, and then the 2 infinite generators / lists with the fizzes and buzzes. And I won't evaluate this, you know what will come out of that. So then the FizzBuzzes is then the zip of the...
Jan, you didn't close the buzzes array.
Where? Yes, indeed. Buzzes. Thank you. Thank you very much. Yeah, so FizzBuzzes is then the combination. We have again a word, we have the word and the number. And if the word is the empty string, then we want to have, we need to convert the number to a string. So let's do it like this. Otherwise, we will use the word. And we want to combine the word and the naturals, starting with 1. So let's format this a bit nicer. So same thing as in Haskell. So we have, if we have the empty word, take the number and return it, convert it to a string. So here with template literals, otherwise display the word. And then it's the only thing that's left to do is we take 101 of those FizzBuzzes, which is just a value, nothing, not a function, and print those. And if I evaluate that now, we get exactly what we expected. So 1, 2, fizz, 4, buzz, fizz, and there the 15th is the 5th buzz. Same solution with the laziness as in Haskell, but you see it's quite a bit more noisy, especially around this next and checking if this is done and then using the value. This is not as nice. Yeah, and this is the result. Quick bonus round. One might argue it's now, because also a common interview question starting from FizzBuzz is, well, how do we write it that you can easily extend it to more? So the thing is now, if you want to have something that's all divisible by 6, should now be replaced with crooks or whatever. Of course, I could now go here, say crooks is cycle, and then repeat 6 times this pattern here, so 5 times, and then crooks, and then again I need to have another zip with. It's not the nicest thing. So let's write us a function called replicate. It takes an integer, some element, and it returns a list of those elements. And replicate basically just does, if we have 0 and we ignore the element, we just return the empty list. And replicate of any other thing, we return, we take that element, we return that element and do this again. So this will now be return a list of just this one element, replicated as many times as needed. So we can, again, this is also defined in the standard library, so I need to hide it. And I could now basically say, okay, this is cycle of replicate 2 empty strings combined with the list as it just does fizz. And this would now be replicate 4 empty strings and then just buzz. And that with that way is way easier to define what for crooks, because replicate 5 plus crooks. And the other thing that's not really expendable is the zip width, because it only takes 2 arguments. So we can basically say, okay, let's define zip width many. It takes an array of arguments and returns something else. And then it takes a list of lists and returns a list of the results. And basically, for zip width, we had 2 separate lists as arguments. Now we just accept a list of those arguments, but the code is basically the same. So if we have just an empty list, we can only return an empty list. If we have at least one, this is now a list of arguments, so we don't even need to have different cases for different things. We call this function and recurse for the rest of the list. And then we can replace this word function with zip with many, and there we can, this will need changing, I will come to that soon. And this will now then be an array. So all the fizzes, the buzzes, and the crooks can then, and the function here needed is just a fold, just like array.reduce. Instead of combining two things, we want to reduce over an array and combine all the things. So we fold over this with ++ and with the empty string as starting value. And if I did not any mistakes now, this should still do the right thing. We load main. It compiles, so that's a good sign. Let's run main. Oops, I did something wrong. Ah, yes, I did something wrong. Fizzes, buzzes, crooks. Oh, yes, I'm stupid. Yeah, this does not work like this. I'm stupid, and I don't have the time to fix this now. So ignore the last part of this. This is stupid. Take the solution from earlier. Yeah, small thinking mistake. Don't try new things during mid-presentation. But yeah, any questions about that now? This is still the solution I wanted to show. Yes. No, the thing is, where is it? Zip with many, where higher. Yeah. So I give it a list of lists. And what I passed in here is I give the fizzes, the buzzes, and the crooks. And then in here, I pattern match basically on the first element in the list, which is the fizzes here. This is, in the first call, this is just the fizzes. And then I call the function with all the fizzes. But I don't want to call the function with all the fizzes. I want to call the function with the first element of the fizzes, the first element of the buzzes, and the first element of the crooks. So I need to transpose. I think there is a transpose function that might work. This is just me spitballing now. This might work. This changed basically a list of lists to change the orders around, and it might be lazy. So this might actually work. I have no idea. Let's try this.
Is this part of the job interview if Jan can return to Munich?
No, there's transpose, but it might be part of... It is part of that. Okay, let's try this. Ha! It does indeed work. So yes. Now we have, 6 is divisible by 3 and 6, so that's why there's fizz crooks. And you see the 15 is unaffected because it's not divisible by 6. Do we have, there is the value. The 30, yes, 30 is indeed divisible by 5, 6, and 3. So indeed, this is working now.
Do we have any questions from remote Stockholm, Berlin, or anybody joining individually? You can also write the question in the chat.
Yes, I will answer.
Yes, we can see the chat here.
Cool.
I think we can all agree that Jan gets to keep his job. It was a well-done interview. Even did the FizzBuzz twice. So maybe that's a race. I don't know. Awesome, if we don't have any more questions now, feel free to ask them in Slack, in Dev General. I'm sure Jan is eager to answer all the FizzBuzz questions. Have a great weekend, everybody. I hope to see you next week.